We would like to welcome you, Professor, and we are looking very much forward to your keynote presentation. And please start. And as I said before, there is a detailed description of you and your presentation in the proceedings. Please, Professor.
Good afternoon, ladies and gentlemen. My name is Xianglin from Tongji University, Shanghai, China. It's a great honor for me to be here in this special way through the web to attend the 5th Symposium this year. Today, I'd like to present you our recent research project on seismic behavior of shear-critical RC columns under different loading directions. The content of my presentation includes the following 6 parts. First, let's see a brief background. Column failure can lead to collapse of structures subject to earthquakes. In fact, earthquakes usually result in 2 horizontal loading actions in columns. This usually causes some more severe damage than a unidirectional loading action. However, most studies on the seismic performance of shear-critical reinforcement concrete columns have considered only their behavior when lateral deformations were applied parallel to one of the column faces. Therefore, the influences of multi-loading directions on column responses to earthquakes are of great importance. Second, experimental investigation. To this end, a comprehensive study was undertaken at Tongji University in order to better understand the behavior of long seismically detailed RC columns under multi-directional loadings. The study included 2 different types of specimens: 10 intermediate shear columns with square cross sections and 8 slant columns with rectangular section cross sections. The main test parameters were shear ratio or shear span ratio, axial loading ratio, longitudinal and transverse reinforcement ratios, as well as the loading directions. More details are listed in this table. This slide shows reinforcement details of aforementioned two types of column specimens. All square sectional specimens were tested in an anti-symmetric double curvature configuration. The specified axial load was applied on the specimen by the vertical hydraulic actuator, acting on the loading frame through the axis of the top section of each specimen. The uniaxial lateral loading was applied by the horizontal hydraulic actuator through the midhead of the column. Any rotational of the top beam was prohibited by the 4-bar linkage. The rectangular specimens were loaded with a testing specimen composed of a universal rotatable hinge and 2 sliding devices. 2 servo-controlled hydraulic actuators were used for the cyclic bidirectional lateral loadings, and one hydraulic jack to apply the axial forces. These figures show the real loading system for R series. The free end boundary condition at the top specimen were achieved by connecting all the actuators to the universal rotatable hinge. The RC column specimen were connected with the universal rotatable hinge through embedded components. Besides, all the actuators were connected to a sliding device at the other end, so that all of the external forces outwards are parallel to their initial directions. Part 3. Experimental results and discussions. The overall crack development process was similar for all square specimens. Take the specimen S2.1 DM13 as an example. In the initial loading stage, roughly horizontal flexural cracks were observed near the top and bottom of the column ends. Afterwards, diagonal cracks developed as the flexural cracks extended from the column edges in the loading direction to the column mid depths. In subsequent cycles, the flexural cracks did not grow further, but instead, several independent inclined cracks formed in the middle portion of the column. During cycles close to the peak strength, several previously formed inclined cracks connected together, and a steep diagonal crack formed. After that, the shear resistance began to degrade, and continued cycling caused the inclined cracks to widen, and the covered concrete began to spoil. The critical inclined crack angle increased with the increasing applied edge loading, and more diagonal cracks were observed for specimens with more transverse reinforcement. For loading from 45-degree direction, the inclined crack angles on sides 1 and 2 of columns were almost parallel to the cracks on sides 3 and 4, but the behavior was asymmetric for specimens subject to 30-degree loadings. This slide shows the crack development at failure patterns for rectangular specimens. In the beginning, the cracks occurred at distances from the ends of the columns, followed by opening of relatively wide inclined cracks near the middle height during subsequent cycles after yielding of longitudinal reinforcements. Failure was precipitated by the widening of inclined cracks, as well as the concrete spalling and crashing in the flexural compression zone at the base of the column. The diagonal crack configuration of RC columns under biaxial shear loading was three-dimensional. The critical inclined crack angle increased with the increasing applied axial loading. As the loading angles changed from 0 degree to 90 degree, the distribution configuration of critical cracks changed from smeared to localized. In this research, key characteristics, including the maximum applied shear, lateral displacement at the maximum applied shear loading, the ultimate displacement and the loss of lateral load carrying capacity, as well as the effective stiffness and degrading stiffness were used here to describe their force deformation responses of test specimens. This table summarizes influences of various factors on seismic shear behavior of tested RC columns. Columns with high axial load and small length to depth ratio tended to have higher shear strength and brittle deformation behavior. Shear capacity and the ultimate displacement capacity of RC columns will dramatically increase with the increasing of the number of the transverse reinforcements. The ultimate deformation of the specimen with more transverse reinforcement were on average higher, and the strength degradation stiffness were lower. The loading direction had a significant influence on the effective stiffnesses at the post-peak stiffnesses, while for shear force corresponding to the first shear crack observed during the experiment, most columns in non-principal directions will reach the same values regardless of the loading direction. The relationship between the loading direction and the normalized shear strength are shown in figs. The shear strength of square columns matched well with the elliptic curves, but the shear strength for rectangular columns did not. For square columns with shear span ratio of 2.1 and long ductile detailing, an increase in the angle of loading direction corresponded to the growth in the shear strength. For other square columns, there was a decrease of approximately 10% when the angles changed from 0 to 30 degrees, while almost no change was observed when the angles changed from 30 degrees to 45 degrees. An optical measurement device was used to track the spatial position of optical marker installed on the test column during the test. On the basis of deformation and measuring method, flexure and shear deformations of test specimens are calculated approximately. This table shows the flexure and shear deformation. We could find that shear deformation should not be ignored, as it is the most dominant component of the lateral deformation for both shear-critical and flexural shear-critical RC columns and multi-directional loading, lateral loadings. For square columns, shear deformations were relatively small in the beginning and grew dramatically to more than 25% of the total lateral deformation when reaching the peak strength, and more than 50% of the total lateral deformation at the shear failure point. For rectangular columns, forming flexural hinges before shear failure occur, the shear resisting mechanisms did not significantly deteriorate, and both flexure and shear deformations increased with displacement demand. The contribution of shear deformation could reach 30% at the end of the test. Part 4. The hysteretic shear model. Based on the experimental results, a simplified hysteretic shear model was proposed. The hysteretic shear model consists of shear primary curve, loading unloading branches, shear failure criterion, and shear failure surface contraction model. The shear primary curve was the envelope curve for hysteretic relationship and was modeled as a trilinear curve including the shear cracking point, shear strength point, and the collapse point. The first stage of shear primary curve represents elastic behavior up to the shear cracking point, which indicates the initiation of diagonal cracks. It is practical to estimate the shear deformation of intermediate short columns by idealizing the column as a homogeneous isotropic material with a constant shear modulus. The second stage indicates the portion from shear cracking till shear failure. According to the experimental observation, shear force transfer mechanisms of intermediate shear columns and multi-directional lateral loadings is similar to the spatial truss, and shear failure occurred after formation of inclined cracks and the yielding of transverse reinforcements crossing cracks. A spatial truss model is proposed here to estimate the shear deformation. The proposed model consists of a diagonal concrete strut, steel ties in longitudinal and transverse directions. It can be further decomposed into a pair of independent planar trusses. Experimental results demonstrated that orientation of the inclined crack plane across the column section is likely to be parallel to the neutral axis. Therefore, the inclination angle of concrete strut in the planar truss can be related to the concrete strut inclination angle in the spatial truss and the neutral axis direction. Assuming the ultimate shear capacity is reached when all cross stirrupers yield. Considering the compatibility condition of planar truss model in both directions, the post-crack stiffness can be calculated. The third stage describes the post-peak shear behavior after shear failure. Assuming that the lateral strength degrades to zero when the column loses vertical load carry capacity, at the lateral displacement is predicted using the actual capacity model proposed by Elwood and Moller. The post-peak degraded stiffness then can be calculated. Osebi and Sansilo's hysteretic shear model was revised and recalibrated in this study to expand its application to the post-peak range when shear strength decay is significant. As shown on this slide, for reference stiffness parameters K1 to K4 are defined to prevent the extraordinary flat unloading slopers. Shear cracking surface at the initial shear failure surface was defined in the 2D shear force space. The calculated shear stiffness was changed only when the loading point intersects with the assumed shear cracking surface or shear failure surface. Before shear cracking, RC column can be thought of as a homogeneous elastic material made of concrete only. Shear cracking strength was estimated using a formula for the shear cracking strength of column in ASCE-ACI 426. The corresponding shear displacement at the cracking point was calculated using the formula for elasticity mechanicals. As for the force-based failure criterion, in order to find a suitable shear strength model for column and different lateral loading directions, a data set including 469 RC columns with square or rectangular cross-section was assembled, including data from peer column dataset database, ACI 369 database, and individual reports. All columns in this dataset were filled in shear or flexure shear mode. Based on the experimental observations, damage photos, and measured transverse reinforcement strength, the critical shear resistance mechanism of each column in the dataset can be further identified as diagonal tension, diagonal compression, truss tension or truss compression. The detailed identification procedure is illustrated in this flowchart. 5 representative shear strength models were selected here to evaluate their accuracy. It was found that the model could provide accurate estimates of shear strength when they were applied to columns that were similar to those used in calibrating each model. However, each model had a significant bias when it was applied to columns with a wide range of characteristics. Some of the methodologies also produced false positives, in which columns were identified as failing shear, even though they failed in flexure. Therefore, we developed a versatile multi-mechanism methodology to estimate the likelihood of shear failure in RC columns with a wide range of characteristics. The methodology builds primarily on the work of Susan and Muller, who developed a procedure to estimate the shear strength of columns controlled by truss tension, and Li and Wang, who developed a procedure to estimate the shear strength of column controlled by strut compression. We added 2 new steps to consider diagonal tension and truss compression mechanisms of failure. The resulting methodology was recalibrated based not only on optimizing the accuracy of the shear strength estimates, but also on the accuracy of identification of the observed shear resistance mechanisms. The ratio of the measured shear strength to the shear strength calculated with the proposed methodology had a mean of 1.01 and a coefficient of variation of 50% for column horizontally loaded in principal direction, and a mean of 1.03 and a coefficient of variation of 21% for column horizontally loaded in non-principal direction. Besides, the ultimate displacement model proposed by Ehnert and Muller was extended into space to identify the failure for column field in flexural shear. Implementation of the proposed model resulted in the mean and coefficient of variation for the ratio of measured ultimate deformation to the calculated deformation of 1.84 with 30% for long seismically RC columns horizontally loaded in non-principal directions. Post-shear failure behavior involves the contraction of shear failure surface toward the actual load failure surface. Many different contraction criteria was considered in the formulation, where it was determined that isotopic-based contraction criterion procedure produced the best element behavior compared to experimental results. Therefore, the isotopic-based contraction model was applied here to describe the post-shear failure behavior. The comparison shows a good agreement between model predictions and experimental results. Part 5, Nonlinear analysis of RC columns and multi-directional loadings. Based on the experimental results, it can be assumed that the loading carrier mechanisms for an RC intermediate short column includes flexural and shear mode. A simplified analytical mode consisting of 2 sub-elements representing inelastic flexure and shear deformation mechanism was developed to describe the hysteretic behavior of RC columns on the multi-directional lateral loadings. The flexure and shear sub-elements connecting in a series to sustain external forces. Deformation in each sub-element is then superimposed for estimating the total deformation. For the flexure sub-element, a modified multisprings model is adopted here. The multisprings model consists of an elastic element representing elastic behavior and two inelastic elements of zero length at both ends, representing an inelastic response in plastic region. Each inelastic element includes a series of concrete and longitudinal reinforcement springs. According to the plane section assumption, once the rotation and the deformation of neutral axis of the section in the inelastic element are decided, the total deformation of the column could be calculated. The proposed shear hysteretic model, as introduced before, is applied here as the shear sub-element. The multi-shear springs model at the uniaxial shear spring are connected in series. Both sub-elements have the same force equal to the external lateral loading. Lateral deformation is the sum of flexure and shear deformation calculated by the flexure and the shear sub-element respectively. Assume the column behavior is initially controlled by flexure. Once shear failure is detected, the degradation behavior is dominated by shear response, and the flexure response keeps the same force with shear response through unloading. On the other hand, if flexure failure is detected, the shear response will unload to keep the same force with flexural response. The analytical procedure for flexure controlled calculation stage at the shear controlled stage are schematically shown on these two slides. The proposed analytical model was applied to 41 columns, including columns introduced before and columns tested by other researchers. All columns were horizontally loaded in non-principal directions. Comparison of external loads and the proposed curves are representatively shown in these figures. Test results are consistently plotted in solid black lines, and simulated results are in dotted red lines. As for our test, the average value of the measured to the estimate peak strength is 1.05, and the coefficient of variation is only 7%. The average value of the measure to the estimate deformation at the strength point at the shear failure point are representatively 1.22 and 1.1.
我进去了，我已经进去了，
the average value of the measure to the estimate
我进去了，我已经进去了，别听了，我在听了。
1.0 as the coefficient variation is only 10%. The average value of the measure to the estimated deformation at the strength point at the shear failure point are respectively 1.39 and 1.12. So finally, let's move to the conclusions and the further research. For the conclusions, the diagonal correct configuration of RC columns and biaxial shear loadings was three-dimensional. With the decrease of shear span ratio, the increase of the axial load ratio at the increase of transverse reinforcement ratio, shear capacity of columns will be increased. The loading direction actually had a significant influence on the shear crack pattern, effective stiffness, as well as the post-peak stiffness. A simplified hysteretic shear model was proposed here in our research project that composed a primary shear force displacement curve and unloading and reloading branches and cyclic loading. A versatile multi-mechanisms model to estimate the likelihood of shear failure in RC columns with a wide range of characteristics was proposed to estimate the shear capacity for column and multi-directional lateral loadings. Comparative results indicated that the proposed numerical model adequately captured the failure modes, peak stresses, ultimate displacement, and strength degradation responses of 41 RC columns failed in shear and fracture shear. The simplicity, accuracy, and computational efficiency of the developed model make it a valuable tool for the assessment of the seismic behavior for existing RC frame structures. In the future, these issues will be further studied. The first one is the mechanism of actual failure. The second one is the uncertainty of failure mode prediction. Third one is the more complex multi-directional loading passes should be used in the test. And finally, improvement of the flow criterion of shear failure surface will be developed, will be studied deeply. Thank you very much for your attention. If you have any questions, it's a pleasure for me to discuss with you. Thank you very much. Thank you again.
Thank you very much, Professor. This is really important for reducing catastrophic accidents of buildings. Thank you. And
Thank you.
Any questions or chat?
Yes, there was a question about the use of high-strength, lightweight aggregate concrete in the use of building and bridges in regions.
Yes, actually, in our research project, only the normal concrete was used in our research project. We did not use the lightweight aggregate, because that should be good in the future. We can study it deeply in the future with the lightweight aggregate to see the differences between this kind of the concrete structures and the normal concrete structures. Maybe we should do something in the future.
There is another question here by Tamon Ueda. Professor Gu, congratulations for the very interesting presentation. I have a question. Under real EQ events, the loading directions are varying. What is the expected effect of this fact based on your research?
Yes. Actually, in our research project, we changed the load directions to see the influence of load directions on the behavior, seismic behavior of the RC columns. They do the load directions do have some influence on the behavior of the seismic RC columns, but in our test only the fixed direction was used. We do not change for the one specimen. We do not change the load directions, but maybe in the future we need to do something to change the the loading paths to see the differences between the the mechanisms or the behaviors of the specimens with different kind of the loading passes.
Okay. I don't see any other questions around.
Okay, thank you.
We thank you very much for your contribution, and we close the session.